Thank you very much. Hi, everyone. Today, Heiko Lohrke and I are going to present our talk, which is about power of optical contactless probing. And we are going to present how we use this technique to attack the Bitstream encryption of modern FPGAs. First, let me start with a story. Sorry. Let me start with a story. Last year at Chess 2016, which was a hardware security conference, we introduced a novel technique, semi-invasive technique against integrated circuit, which was based on optical contactless probing, which is a known failure analysis uh, technique. And we showed that actually we can, probe and extract secret data and on-die and volatile secret data on the FPGA in a contactless way. And we have done this experiment actually on a 16 nanometer FPGA from Altera. And then after we introduced the attack, people, came to us and said, your attack is really interesting, but there are a lot of challenges. First of all, chip preparation is really challenging because for our attack, actually, at that time we need to, depackage the plastic of the chip, and then from the backside, and then we polish the silicon substrate to conduct our attack. So they said it's not easy. Second, they were telling us that localization and finding the security related part of the circuit is a time consuming. If you have millions of transistors and gates, it might be infeasible to find the points of interest on the chip. Third, they were telling us that you have conducted your experiment on a 16 nanometer chip, but nowadays the chips technologies are much smaller, like 20 nanometer or 28 nanometer. So it might be also infeasible to port or to actually conduct the same attack on the smaller technologies. And finally, the equipment which you need to conduct such attack is actually really expensive, and not all hackers or attackers can have access to this equipment. In this talk, we are trying to assess the accuracy of these beliefs. But let me first introduce the technique itself. You can see a simplified image of the setup. We have a light source. We illuminate with the light beam the transistors on the chip, right? The transistor they became warm, and then partially the light will be reflected, and we can detect the reflected light by detector. And we know if we change the voltage of those transistors, the absorption coefficient or the refractive index of the transistor are changed, which means the reflected light, the intensity of the reflected light will be also changed. That means we can, probe uh, probe the waveforms or signals which pass through a transistor, and it behaves like an oscilloscope. And without any contact to the wires and transistors, we can really extract the waveforms. This technique is actually called electro-optical probing. Um, but there is another technique which helps us actually to localize the points of interest, which is called electro-optical frequency mapping. In this case, we actually fed the light back to a narrowband filter, and then we give it to the spectrum analyzer. In this case, we can actually localize all transistors or all gates which are switching with the same frequency. Okay? So this is the technique. This is a brief introduction for the technique. And as a target, actually, we have selected field programming gate arrays or FPGAs because they are primary components in many different applications, from telecommunication devices to defense-graded products to space applications. And now recently, Amazon and Microsoft, they have also started to integrate FPGAs to their cloud computing platforms and use them for machine learning approaches. They might be also considered in future for automotive applications, but there is a security concern about FPGAs. Um, the binary which configured the FPGA is called actually Bitstream, and so it contains intellectual property and a lot of secret information which shouldn't actually be exposed to an attacker or to an unauthorized person. But since most FPGAs or since most of programmable SoCs are SRAM based, which means they don't have any internal non-volatile memory, the beta stream should be actually stored in an external NVM. And upon each power on, the beta stream should be loaded from the NVM to the FPGA to configure the FPGA. Um, so basically, because we are in the field, it might be an adversarial environment, and the Bitstream is actually loaded in an adversarial environment. We have also flash-based FPGAs, but still, they can, of course, keep the configuration inside the package, but they might need some update in the Bitstream from a remote server. Again, we have the problem that Bitstream should be loaded in an adversarial environment. And the problem is that if an attacker can eavesdrop the Bitstream, she might be able to clone, reverse engineer the design, tamper with the design, or even spoof the design. Conventional solution is actually to encrypt the Bitstream. How does it work? So I'm an engineer. I'm the designer of the application. So I load the secret key in a trusted field via JTAG to the FPGA. The secret key will be stored in battery-backed RAMs or eFuses of the FPGA. And later in the second phase, I have my design, which I want to protect it. I just encrypt my design with the secret key by an AES encryption, which is provided by the FPGA vendor. And then, sorry, and then I store the encrypted design in the external NVM, which coexists with FPGA on the same printed circuit board. Now we are in the untrusted field, and so the Bitstream, the encrypted Bitstream, is actually loaded to the FPGA. So the secret key which we actually stored in the FPGA is used by ASIC AES decryptor on the chip to decrypt the encrypted Bitstream. So the plaintext data will be generated, which contains all IPs and secret data, and the FPGA will be actually configured. So in this case, we in order to assess or address those beliefs which I mentioned in the first slide about the hardness of this attack, we conducted a case study on an FPGA, and when we wanted to see if we are able or if an attacker is able to use this technique to localize the output of AES decryptor on the FPGA and probe the whole secret data from the FPGA using optical contactless probing. So in this case, the attacker should actually get a training device, which is of course feasible because you can go on in the market and buy an FPGA, then you can have it, and you can do a lot of experiments. You have a lot of time to do experiments with this device. And the first step would be to find the configuration logic on the device, on this FPGA. Because when you find the configuration logic, then the next step would be to find the decryption core, or the AES core in our case, on that area. So by finding the decryption core, the next step would be actually to find where the plaintext, where are the outputs of these decryption core, because there actually is our point of interest. There, the plaintext is actually generated, and we are interested in the plaintext and the design of the FPGA. And finally, the attacker needs to extract or probe these secret data from the FPGA. For our experiments, we have used Xilinx, Xilinx FPGA. More precisely, it's Xilinx Kintex 7, which is manufactured with 28 nanometer technology. The technology is small enough to show the powerfulness of the attack. And later, my colleague Heiko will explain you why we, in this case, we didn't actually prepare the chip. For example, we haven't to do depackaging, we haven't to do silicon polishing because the chip was flip chip, and the silicon, as you can see in this image, is uh, exposed to the attacker. And for our optical setup, we have used a Hamamatsu Famous 1000, which is a common failure analysis device. And the laser wavelength which we have used has a 1.3 micrometer. And interestingly, our laser spot size is larger than 1 micrometer. So you can see the resolution, our optical resolution is much, much less than the chip's technology size. And now my colleague Heiko will explain the attack in details.
Yeah, thanks, Shahin. So as Shahin has said, the first step will be localizing the configuration logic. And what you can see in this image is just a photograph of the chip's package. And the green area on the outside is something that is called an interposer. This, you can imagine this to be just a small printed circuit board. And then what you can see here in the middle, this bluish rectangle, is actually exposed silicon. It has a few device markings here, but this is actually the die of this chip directly exposed. And that is the case for all of these flip chip packages in general. And now, to localize the configuration logic, an attacker would probably first take the failure analysis microscope and take reflected light images. And because we are using this 1.3 micrometer wavelength, silicon is totally transparent to that. So this, what looks a bit like a piece of metal here, will become totally transparent as soon as you put it under your microscope. So this will then look like this. You can still see the device markings, of course, because we haven't touched the chip at all, but the silicon becomes like glass. You can directly look through the silicon, and then here in the background, you can see the structures and circuits which make up this FPGA. Now, I won't go into too much details on how you can then actually distinguish the configuration logic. I will just give a very general explanation, and for more details, you can look in the paper. But if you look at this picture, I guess you can see there are some regular stripes here. And if you know about FPGA design, if you're implementing something on the FPGA logic, the FPGA logic fabric consists of many identical structures repeated over and over again. So if an attacker looks at this, he can immediately say, okay, everything that looks super regular will not be the configuration logic, it will be the logic fabric. And then you have some areas remaining, for example, like the ones here and the ones here in the middle, which are more irregular. And these are candidates for containing the decryption logic. And then in combination with the data sheets and the details on the paper, you can actually find out which is the best candidate for the configuration logic. And actually turns out it's this ASIC in the middle. Then if we zoom in on this ASIC, this is what it looks like. And if you have a bit experience with patterns, you can already see this, like, it's just experience. This is what synthesized logic looks like. If you have a certain function and you throw it through synthesis, it will look like this because of the algorithms used. And you can see there's a second area or maybe two areas over here which also look like they contain a certain function. So now we have found the configuration logic. We actually verified before we continued that this is the configuration logic. Again, some details for that are in the paper, but we were sure that this is the configuration logic area. Now, if you recall, the next step would be to find out where actually the decryption happens. And since we have this electro-optical frequency mapping, this is rather straightforward, and I hope that actually you will be able to find the decryption core in a few moments. So what we did was we performed electro-optical frequency mapping measurements at the clock frequency. So the clock is externally available, and electro-optical frequency mapping will show you all transistors and gates operating at this clock frequency. So we thought, well, we could just compare these activity patterns for encrypted and unencrypted bitstream and see if that gives us any hints. So in this image, this is the result of such a measurement for the unencrypted bitstream. This is the same area, faintly in the background, a bit darkened to increase visibility of the actual measurement. You can still see the reflected light image. So here's this larger block, and here's a smaller block. And the green pixels are the areas where the electro-optical frequency mapping has detected activity at the clock frequency. And as I said, this is at the unencrypted. This is for an unencrypted bitstream. You can see this block, there seems to be something going on here. This block, not so much, a little bit of activity here, some random noise. Now, if we switch to encrypted bitstreams, this looks like this. And I guess, who can guess where the decryption core is? It's this one. So this is rather straightforward. If you have, and this shows how powerful this setup is in the hands of an attacker. And these are commercially available setups that are already everywhere where failure analysis for silicon devices is done. Now, the next step is, now we know that this is the decryption core, we have to go in and actually find the plaintext. And that is not as forward, so I have to digress, as straightforward, so I have to digress a bit on, let's say thinking in the frequency domain, because after all, we are detecting frequencies. So this is a simple example which I will give, where we assume that all data is transferred in a serial fashion. If you look at the paper, it also works if the data is transferred in parallel fashion, but I think this is the most easy to understand. So let's assume you have this setup that Shahin has already explained. And now an attacker, because he's still on this target, on this training device, crafts a manipulated bitstream. And he crafts this bitstream to be time periodic. So if you transfer this bitstream in a serial fashion, it will generate a fundamental, all the gates transferring this bitstream will switch with a fundamental frequency which has a period of 2-bit length. Because every transistor will be on, off, on, off, on, off. It will generate a very specific frequency. Now, if you encrypt this, all these structures, frequencies, and pattern vanish. That's actually a very nice property of the encryption algorithm because it prevents frequency analysis and other attacks like that. But of course, when the device decrypts the data again, then exactly this bitstream will be recreated. Now, if we look at this in the frequency domain, for this encrypted bitstream, it is, to our purposes, indistinguishable from noise. So the time domain signal will be indistinguishable from noise, so its frequency signature will not contain any peaks. There will be no frequency signature, and there will be no dominant peaks. There will be no fundamental frequency generated. Now, this encrypted bitstream goes into the device, travels around the device, does whatever, and then only as soon as it is decrypted, this data will be regenerated. And as soon as that happens, you have a time periodic function on every transistor carrying the plaintext. And that means that every transistor carrying the plaintext will be immediately detectable if you set your electro-optical frequency mapping to this fundamental frequency. So you will not see anything until the data is decrypted. And as soon as it is decrypted, it will just pop up in the EOFM measurement. Now, as I said, this is a simple example for a serial bit stream for the sake of simplicity. This also works if you have 32-bit buses or wider buses. You can imagine you can do this for individual bus lines. The concept stays the same. As I said before, for details, look in the paper. We actually found out during our measurements, actually, if you use this, it's very easy to verify if you have a 32-bit bus or if it's serial. Because if you assume this, you do your measurement, you see nothing, your assumption is wrong. You try another assumption. As soon as you see something, you know, okay, this is a bus with 32 bits, for example. In our case, we found out, okay, the output is 32 bits. And for the measurements that I'm about to show you, we did something a bit special because it looks nice, and also we needed to map the individual bus lines. So what we now did was we only generated these fundamental frequency signatures on single bus lines. And this is what I'm about to show you. So we did 32 measurements for the 32 bus lines, and only for every measurement generated the fundamental frequencies on one of the bus lines. And in a moment, I will start this animation. And you can see here is the bus line number. Again, this is in the background. In dark, you can see a reflected light overview image just to aid orientation. And all the green spots is activity, but only for that certain bus line. And then this is animated for all the 32 bus lines. And this is at the plaintext frequency. So all these green spots that you can see here potentially carry the plaintext data. So, and this is what it looks like. And if you look at this closely, you can see that there's an area down here which looks pretty odd. So you see bus line 0 is next to bus line 1 and so on. They just increase. So this is probably an output port. So there you have it. That's where the plaintext is leaving your decryption core. If for some reason, and this is probably the best place to probe your data, but what you should also notice here is if for some reason you can't probe here, inside the synthesized logic mesh, there are also places which carry the plaintext data, which makes sense because there will be transistors feeding the output port. And usually, if you ask someone, hey, could you reverse engineer a single transistor carrying a certain type of data in a synthesized logic mesh? They would say, no way, it's impossible. This measurement takes 2 hours. So you can see you have additional probing locations here. You see also there are some false positives because they stay on all the time. These are just spots which happen to be at the same frequency by coincidence. So you can ignore them because you see there's no dependence on the bus line number. And what we also found out is that actually the data gets fed back after decryption to the main core, which makes sense because the main core is doing the interpretation of the bitstream data commands. And because the decrypted bitstream has exactly the same format as the normal bitstream, it makes sense that you use the same logic to interpret the decrypted bitstreams as well as the bitstreams which were not encrypted in the first place. And yeah, this is an animation for the main core. You can see that this is not as ordered, so you can't really find an input port. But for example, in this area, you can see that there's some data dependency that moves down here, and also again some false positives. So even if option A and option B failed, you could also go back to the main core. And then we performed our measurements actually at this output port because it was the most straightforward way. So this is an example of then extracting this data using electro-optical probing. That is then rather trivial because you just need to aim your laser at this location and then you can extract the data from the individual bus lines. It's, as Shahin said, it's like an oscilloscope, but you have a laser probe head. This is just for 2 of the 32 bus lines. This is bus line 0. The data is actually 0, 1, 0, 1. And then for the bus line 2, the data is 0, 0, 1. And IS outputs data in 128-bit blocks. We have a 32-bit bus, so that means there have to be a burst of 4 words on the bus. So you can see this is where word 1 is transmitted, and then the other 3 words. And then after that, the IS is busy decoding the next block. And when the next block becomes available, there will be another burst of 4 words. And in this way, an attacker could read out the plaintext data from the device if she probes the data for all 32 bus lines. Now, what we also wanted to do with this work was to assess, apart from what's possible with this attack, how much effort an attacker actually has to put in it. And for this, we precisely measured the time that it took us on the lab equipment. We installed time tracking software on our lab equipment. And actually, the complete attack development took 10 days, 74.9 hours. And you have to remember, an attacker has to do this only once. Every chip of this die type is the same. As soon as you have found these points in any new chip that you steal from someone, you can just directly go and extract the data. And if you calculate how much this would have cost if an attacker would have rented the equipment, our equipment, for example, can be rented for $300 an hour, including operator. And this then amounts to $22,500 for the total attack development. Again, that's a cost that you have to pay only once. And additionally, you might even build these setups yourself. They have been built for $20,000 to $30,000. Then you have to add a bit for the optical probing. But yeah, that's also an option for an attacker. So you see, it's not as we were very surprised. It was especially about the time. It was the second time we did such an attack. It was much less than we had expected, which shows how powerful these techniques can be. So to conclude, if you recall the common beliefs from Shahin from the first slide, this attack was actually much faster than we had expected. As you've seen on the previous slide, it was much cheaper than what we had expected. And a very important thing is, and a very common misbelief is, it makes no sense at all to compare technology node sizes to optical resolution. That just doesn't make sense at all. So please, if you see anyone saying that, show them this work. The people who really do security on this hardware level, most of them know, but it's a very common belief. You can see the resolution that we had is 2 orders of magnitude larger than the technology size, and it still works. Usually you have people saying, oh, it's 28 nanometer, you have 1000 nanometer, this will not work at all. You see, it can be done in 10 days. And we did mount this attack in a non-invasive way. We did not touch the chip package at all. So you just put it under the microscope and do your measurements, and that's it. And we strongly believe that if this is not addressed, these techniques will continue to be a threat in the future, or will become a threat in the future. And in our paper, we have detailed some countermeasures which are able to completely block these attacks. Some of our colleagues are actually working on that to protect the backside from all optical attacks. So if you want details about that, please look in our paper and you can find the reference to their work. And this concludes my talk. I'd like to thank you for your attention. If you have any questions, feel free to ask them.
Hi, great talk. Daniele Fronte, ST Microelectronics.
Sorry, can you speak up a bit?
Daniele Fronte, ST Microelectronics. Thank you for your talk. Did you try or are you going to perform this attack on a secure microcontroller?
On a CPU? Will we? Probably. Actually, we did not do this on a secure microcontroller so far because we worked with FPGAs before, and we already had the experience, and the FPGAs already contain decryption ASICs. So this was kind of the easiest route for us to take. But of course, it makes sense to test if, for example, the additional countermeasures that might be present in a secure microcontroller might hinder your attack. I would expect them to not hinder you because also a very common misconception with this wavelength that we've used, 1.3 micrometer, there are no sensors which can detect this, at least not light sensors, because the photon energy is lower than the silicon band gap. So a photosensor will not generate any photocurrent. And then again, it's a scanning technique. So you can just scan the area where you want to attack. If you see the sensor, you just don't scan on the sensor, and then it will not receive any light, as opposed to like an optical microscope. But that's something that we will look into in the future.
Hi. My question is, you constructed these very careful plain text to find the bus lines and everything. Would the attack be completely infeasible if you couldn't control the plain text in such a way, or would it just take longer?
The thing is with this, especially with FPGAs and with these low-level, transistor-level hardware attacks in general, it is enough if you have any device of the same type. It doesn't have to be your target device. You just buy an FPGA, and all FPGAs of this type will be the same. So you have all the time in the world and all the control. And again, what you're finding is 32 locations. And if you have these 32 locations on your training device, which you have full control of, you move to your target device. It is more difficult if you don't have control of the plaintext, but if you look at our chess paper, there we didn't induce this frequency using plaintext control, but instead we used a trick which we called basically a reset loop to induce certain frequencies. All of this is just, if you can think of something to identify your area of interest in the frequency domain, you can do it. So if you know a register is loaded with a certain frequency,
May I add something? This is actually more. It's like a profiling attack, which also in the power analysis, for example, people do. So it's, as Heiko said, we just try to understand the device and then apply it to other devices. So we are not, for example, trying to extract here some other stuff like the key itself, but just to understand and reverse engineer the underlying hardware.
Hi, David Gens, TU Darmstadt. Awesome talk, really cool work. My question is, you said in the beginning that for the optical probing, you had the clock of the FPGA externally available. Could you talk a little bit about if this is not the case?
Yeah, actually, that's one of the countermeasures that we propose. But there are ways around it. It just makes it a lot easier, and the ways around it are not that complicated. So this is not the clock of the FPGA. Actually, it is the configuration clock. It's the clock that is used to clock in the data. So it's not the real master clock. But as you see, because there are circuits in there that have to deal with the input data, it still works. So you need this clock to input the data. So it has to be externally available. So we've detailed some countermeasures where you could unlink this. But in the past, we have also done in the chess paper for profiling of ring oscillators, which are running in a device. There you don't know which frequency they might have if you don't have an output available. But you can do, for example, power analysis in the frequency domain on the power supply rail. And then if there's something running, for example, the clock will probably draw a lot of power because all the clock buffers will switch all the time. You just buy a cheap, that's what we did. We bought a 13 euro RTL SDR, software-defined radio, and analyzed the supply line. And then you can see where the circuit is operating. And then you can use these measurements. You don't have to be exactly on the frequency. You can narrow it down with further measurements. But it helps a lot if it is available.